I'm Bob Swanson. I am the designer of this astronomy course. I may not be the instructor for your particular section, but I did design this, and I wanted to first of all welcome you to astronomy here at ICC, as well as I wanted to explain what these lecture mixes are. I've created these lecture mixes to give you some context for what you're going to be learning in this module, very similar to if you were in a traditional class and you would be coming to lecture. Now, of course, I want to explain what these are as well as what they are not. They are not a replacement for your textbook. Make sure you get the textbook and that you're reading it on a regular basis. I'm not going to give you all this information in a lecture mix. What I'm going to do is I'm going to provide you some extra material, some extra demonstrations, some extra examples to help to kind of pad out what you're learning in the textbook. So it's not a replacement for the textbook. It is a supplement to the textbook, and I do hope that you use both of these to their greatest extent. Use the textbook, use these lecture mixes to get some context for what you're reading. Now, as far as the content of Module 1, Module 1 covers chapters 1 and 2 of the textbook. Here and Now, as well as, I think, Motions of the Sky or something of the sort. Here and Now deals with the scale of the universe, the fact that it's huge both in distance as well as in time. This part 2 is about essentially the motion of the sky, and you're going to be learning about what's called the celestial sphere. Now, there are some basic motions of the sky that you have to understand. You have to understand the fact that the Earth is rotating on an axis, and the Earth is going around the sun. And you're going to learn about that in a song, actually. And then the sun, of course, and the solar system is moving around in the Milky Way galaxy. And the Milky Way galaxy itself is moving through space as well. So there's a lot of motion going on when you get into astronomy. Now, one of the basic motions, as I mentioned, is the fact that the Earth rotates. And that's what you can see, maybe, in the celestial sphere here. Now, the celestial sphere comes in handy because it allows us to show how the sky moves. Of course, the sky moves because the Earth is rotating, but sometimes it's useful to just pretend that the Earth is fixed and that the sky and the stars are actually moving westward through our sky. So the Earth is rotating eastward, and by virtue of the fact that it is rotating eastward, these stars appear to be moving westward. And that's really the key to most of Chapter 2's material. So anyway, that's at least a little bit of a context of what you'll be learning. Make sure to go through all the slides, make sure to answer the quiz questions, and of course, look out for announcements about joining some online study sessions. I'm not probably making big news when I tell you that space is indeed very large. Think about how we measure distances here on Earth. Typically it's in miles or kilometers, and it's actually a good time for me to talk about miles and kilometers. How big is a kilometer? Because that's actually the preferred unit in science. Metric units are preferable to English units. So what's a kilometer? A kilometer is 0.62 miles, so it's a little over half a mile. So think about if you run a 5K race. You actually run about 3 miles. So 5 kilometers is approximately 3 miles. A 10K is approximately 6 miles, etc. But notice that these units are pretty small when you think about them in space terms. So notice that even when we just talk about things that are relatively close by, like the moon, just to the moon is 380,000 kilometers. When you start talking about how far away the sun is, 150,000 kilometers. Notice how many zeros you have to throw in there. If you were to write this out all the time, it would kind of kill your hand. So therefore, we're going to introduce the topic of scientific notation in some of the questions you'll be answering for your quiz. So make sure to review the section on scientific notation. There's also information about scientific notation in Appendix A of the textbook, so I encourage you to review that information. But what we'll quickly find out is that kilometers, miles, these are not good yardsticks or distances of measure when you start talking about space. You have to actually start using different yardsticks. You have to use larger increments of distance in order to describe the huge distances in space without having to resort to having huge numbers. And so therefore, astronomers use other distance measurements such as astronomical units. They use light years. And as we're going to find out much later in the course, they actually measure distances in what are called parsecs. For the time being, at least understand what an astronomical unit is and understand what a light year is, as those will be very important as we move through the early part of the course.
Whenever life gets you down, Mrs. Brown, and things seem hard or tough, and people are stupid, obnoxious or daft, and you feel that you've had quite enough, just remember that you're standing on a planet that's evolving and revolving at 900 miles an hour, that's orbiting at 90 miles a second, so it's reckoned a sun that is the source of all our power. The sun and you and me and all the stars that we can see are moving at 1,000,000 miles a day in an outer spiral arm at 40,000 miles an hour of the galaxy we call the Milky Way. Our galaxy itself contains 100 billion stars. It's 100,000 light years side to side. It bulges in the middle, 16,000 light years thick, but out by us it's just 3,000 light years wide. We're 30,000 light years from galactic central point. We go round every 200 million years. And our galaxy is only one of millions of billions in this amazing and expanding universe. On expanding and expanding, In all of the directions it can whiz, as fast as it can go, at the speed of light, you know, 12 million miles a minute, and that's the fastest speed there is. So remember, when you're feeling very small and insecure, how amazingly unlikely is your birth. And pray that there's intelligent life somewhere up in space, 'cause there's bugger all down here on Earth.
Okay, so I hope the song played for you, but even if it didn't, I wanted to go through some calculations. This is a little more inside baseball. This is not stuff you would need to be able to replicate on a test or a quiz or anything like that. But I want you to at least get a feel for some of the sizes, the speeds at which things move in the cosmos. And Eric Idle does a great job in the Galaxy song of pointing some of these out. So the first thing that he mentions is he says that imagine we're on a planet that's evolving and revolving at 900 miles per hour. And one thing I do take issue with, I wish he hadn't said revolving. What he really wanted to say there was rotating. The Earth is spinning, and he's saying that it's spinning at 900 miles per hour. The question is, how would you figure out whether he's right or not? You know, he's just a songwriter. Is he really correct? How can we determine that? Well, he's throwing out a speed. He's throwing out the speed at which we are spinning. And he says it's 900 miles per hour. How do you find out a speed? Well, if you've taken any physics or physical science in the past, you hopefully know that speed is distance divided by time. For example, if I'm driving at 60 miles per hour, that means that I cover a distance of 60 miles in 1 hour. So speed is really distance divided by time. So what he's saying is that the Earth is indeed spinning at 900 miles per hour. So in order to tell whether he's correct or not, I would need to know how far we travel in a certain amount of time. Well, when it comes to spinning, how long does it take the Earth to spin like once on its axis? Well, that by definition is a day. So I'm trying to draw a very poor-looking Earth here. There's my Earth, and that's just kind of, I'm drawing in the equator of my Earth. Can you imagine if I'm, put my guy in, I'll put a guy in blue. I've got a guy who's standing at the equator. There he is. And without him doing anything, with him just standing in one place, do you acknowledge or recognize that the Earth will cause him to move? Because he's attached to the Earth is going to spin, and will spin one full time in 24 hours. So therefore, we could figure out the speed at which that guy is moving if we, first of all, use the time as 24 hours. So that's part of our speed calculation, as that he's going to travel around the circle in 24 hours. The question is, well, how can we determine how far he has traveled? That's a little trick here, and it takes a little bit of geometry. If you perhaps recall from maybe a slide or two ago, I believe I think I had the diameter of the Earth thrown in there. The diameter of the Earth, if I were to start to dig from any location on Earth through the center of the Earth and get to the other side, I would have to dig 8,000 miles, approximately. You know, I'm going to round off a little bit. 8,000 miles. So therefore, I've got a circle here that has a diameter of 8,000 miles. Now, do you remember from geometry a relationship between the diameter of a circle and the circumference of a circle? Because do you notice that I can figure out the distance this guy travels if I figure out the circumference of this circle? Well, circumference is sometimes given as 2 pi r. You may have seen that before, 2 pi r. Or it's also given as pi d. Recall that r is radius, d is diameter. And we just said the diameter of the Earth is 8,000 miles. So therefore, the circumference winds up being pi times 8,000 miles. Well, what's pi? It's 3.1415, etc., etc. Let's just call it 3 between friends. And therefore, I'm going to multiply 3 times 8,000 to determine the circumference of the Earth. So what does that wind up being? So wouldn't that be the distance that he travels in 24 hours? So therefore, he travels 24,000 miles in 24 hours. So what does that give us? Oh, that gives us 1,000 miles an hour, doesn't it? That's how fast our guy travels. Now, our songwriter, Mr. Eric Idle, said that the Earth is spinning at 900 miles an hour. Is he wrong? No, he's in the ballpark, isn't he? But is he wrong? Well, actually, I would say that he's not, because, well, first of all, we did some rounding, right? We rounded the diameter of the Earth. We rounded pi, so mathematically we did some rounding. But more importantly, do you notice that Eric Idle has a accent? Yes, indeed. And therefore, Eric Idle's probably not at the equator, right? He's a British guy. He's at a higher latitude. So he may be somewhere up here on Earth. I'm going to draw in the circle that if Eric Idle were going around, he'd be up here in the northern hemisphere somewhere. Notice that his circle doesn't have quite the same diameter, and therefore not quite the same circumference. He's still going to be traveling once around that circle in 24 hours, but his circle's going to be smaller. So sure enough, he might wind up with a value slightly less than 1,000 miles per hour. So 900 miles per hour, we'll take it. That's the rotational speed of the Earth. So that's pretty freaky to think that we can just by virtue of us being attached to the Earth, we are actually traveling at hundreds of miles per hour, and we don't notice it. Now, he threw out another number, which was the speed of the Earth through space. So that the Earth and you and me are traveling at 19 miles a second, so it's reckoned, around the sun. So how can we figure out whether this is true? And again, just put that number into perspective. 19 miles a second. He's saying that the Earth is hurtling through space at 19 miles per second. Well, gosh, how fast is that? Well, if you live in northeast Mississippi, which is where I live, I know that ICC, our college, has two campuses. It's got the Fulton campus, it's got the Tupelo campus, and they are both separated by about 19 miles, 20 miles, thereabouts. So that means that the Earth hurtles through space a distance from Fulton to Tupelo in 1 second. Now, is that correct? How would we know? We can play the same game. Remember, the Earth goes around the sun. I'm going to draw my little sun here. And the Earth goes around the sun in approximately a circular orbit. So there's my Earth. And it's going to go around the sun in an approximate circle during the course of a year. My circle's not that circular, but imagine that's a perfect circle. Now, the question is, how can I tell if he's giving me the right number? I play the same game. Remember, we have this speed equation, distance divided by time. The time, again, is the easy part. I know how long it takes for the Earth to go around the circle one time. It's a year, which is 365 days. The question is, how far do I travel? What's the circumference of that circle? Because again, it's a circle. So again, I play the same game. Circumference is pi d, or 2 pi r. And the question is, okay, what's the radius of this circle? In this case, I don't want the diameter. Actually, I'm going to go for the radius, because actually I know this. Actually, this was a couple of slides ago. You saw this. The distance between the sun and the Earth is 93 million miles. And let's just call it 100 million miles between friends. Why not? So 100 million miles is how far the Earth and the sun are separated. So therefore, that gives me the radius of the circle, does it not? 100 million miles. And now you can see all these numbers. It's so difficult for me to draw these in with a mouse. Why scientific notation comes in so handy. But anyway, how far? We got 2 pi r, 2 times 3. I think I'm going to use 3 as pi, just for speed purposes. And times 100 million. So that winds up being, I'm just going to write 100 m for, so it winds up being the Earth travels 600 million miles in 1 year. Too bad we don't get frequent flyer miles for that. The Earth, and again, we are doing that as well. Just by virtue of you standing here on the Earth, being attached to the Earth, you actually travel 600 million miles a year. So that goes then in the numerator of our little fraction to calculate the speed. And one thing I can tell you is that 600 million divided by 365 is not 19. Right? So he gave us the answer of 19 miles a second. It turns out that it winds up being a much larger number. It's like 1 4, 3, 8, 3, etc., etc. 5, and that's miles. But that's the problem. Notice that my calculation is in miles per day. He gave it in miles per second. So, in order to really compare apples to apples, I would need to convert this. I need to go from miles per day into miles per second. And you can do this if you recognize that there's 60 seconds in a minute, 60 minutes in an hour, and 24 hours in a day. It turns out that you would wind up with 86,400 seconds per day. So in order to really compare our values and see if he's right, you would need to divide this big number by 86,400. Then you'll be comparing miles per second. And it turns out that, yes, he's about right. It's about 19.3 miles per second. So sure enough, good for you, British songwriter. He gave us another good number. The last thing he mentioned was the speed of light. And this is something we're going to be coming across several times. First of all, in this chapter about how fast light travels. The speed of light is, well, gosh, he said it's 12 million miles a minute. How will we determine that? Well, it turns out that the sun, and this is I think a question you're going to wind up facing in one of these slides here. The light that we receive from the sun at this instant actually did not leave the sun at this instant. It actually left 8.3 minutes ago. It takes time for light to travel. This is a huge distance. 100 million miles is a long distance. So even though light travels really fast, it doesn't travel at an infinite speed. It takes time for light to travel that distance. And sure enough, it's about 8 minutes. So to find out the speed of light, then I can divide the distance that light travels, which we just said is 100 million miles approximately from the sun to the earth. And I can divide that by how many minutes it takes, which is about 8.3 minutes. And if you do the math, divide your distance by your time, you'll wind up with 100 million divided by 8.3 is going to be about 12 million miles a minute. So in any case, good old songwriter is correct. And you've learned a little bit, not only about the huge sizes in space, but also a little bit about how to calculate velocity or speed, and also how to do little unit conversions. So I hope it was worth your time to sit through this little video. For me, one of the coolest things about astronomy is that it actually allows you to do some time traveling, because the distances in space are so huge, and the way we gain information about other objects in the cosmos is via light. It's from the light they produce. And light, as we know, travels at a finite speed. And therefore, when we see stars in the night sky, or even our own sun, as I already mentioned, we're not actually seeing it as it is right now. We're seeing it as it was, in the case of the sun, 8.3 minutes ago. So the sun could actually blow up, like right now, we wouldn't know about it for another 8.3 minutes. Isn't that fantastic? And therefore, of course, that's our nearest star, the sun. When you start talking about stars and galaxies that are farther away, that means we're seeing those objects as they were much earlier in time. And we've been able to observe, and this is getting into cosmology, which is farther in the course, but the present motion of galaxies that are really, really far away, we can actually kind of run the movie backward and come to the conclusion that everything started 13.7 billion years ago. That's really awesome. As far as humans, gosh, we've been around for a long time. Civilization, yes, about 10,000 years, but even before that, the human species, Homo sapiens, has been in their present form for anywhere from 100,000 years to about 250,000 years ago. We've had hunters and gatherers that essentially were the same species as we are now. That's pretty fascinating as well.
Okay, if you recall, I just mentioned the fact that astronomy allows you to do some time traveling. So let's play around with this concept. We've got this guy who's looking at a star, And he's looking at it in 1200 AD, and he sees a star, and the star turns out to be 3,000 light years away. So now let's allow this star to explode. When a star explodes, it's called a supernova. So we're going to go ahead and let the star go supernova. It's going to explode. Remember, it's exploding here in 1200 AD, and he's observing a star 1200 AD. The question is, when is he actually going to see the explosion? Kablooey. So notice the star explodes in 1200 AD. He does not find out about it until 3,000 years later. In 4200 AD, finally, he sees the explosion. So again, astronomy is time travel. We don't see those objects in the sky as they are right now. We see them as they were, and of course, as they were depending on how far away they are from the Earth.
As you've read in the book, the constellations are usually Latin names or Greek names, and they used to be essentially patterns in the sky or kind of pictures in the sky. And in more modern times, there are 88 official constellations, and instead of being like pictures or shapes, they're actually kind of like states. What astronomers have done is they have actually taken the entire night sky or day sky and parceled it out into essentially like states, just like the United States is made up of 50 states. And there's not one part of the United States that's not within a state. And similarly, there's not one location in the United States that's in more than one state at a time. So, for example, Tupelo. Tupelo is definitely in Mississippi. It's not in Tennessee. It's not in Arkansas. It's not in Alabama. It's only in Mississippi. In the same way, the sky has been parceled out so that whether there's a star there or whether there's a star that's visible to us here on Earth, or maybe there's just nothing there, but still that part of the sky is part of a particular constellation. So again, there are 88 essentially states in the sky. We call those constellations.
Okay, so if you were in class with me, you would most likely be using a virtual planetarium program called Stellarium. And so I wanted to introduce this to you. Stellarium is a free download for a desktop computer. There are also apps for Stellarium, which I believe are a couple of bucks. You don't have to use Stellarium. You can really look into any particular virtual planetarium program. There's a lot of them out there. This is the one I'm just most familiar with. But the cool thing about Stellarium, and I'm not going to show you all the features, is that it allows you to look at the sky in any direction and from any location on the Earth, and really from any time you want. So I'm actually just recording this right now in December of 2015. Again, it doesn't really matter. You can look in any direction. Of course, I'm recording in the daytime. The cool thing about Stellarium is you can advance time. So I can actually take things into the evening hours here just to show you what our night sky would look like this evening at around 9 o'clock. And I'm not going to, like I said, go through all the bells and whistles, but I did want to show something about constellations and asterisms, since that's the topic. And you can actually put on constellation lines. You can once I put on my constellation lines, hopefully you notice a couple of constellations leaping out at you. If you want to label them, you can do that as well. Notice what we are seeing immediately is you should notice a couple of spots in the sky that you may be familiar with. Notice that just creeping up over the horizon now is the Big Dipper. That's an asterism, because it's a pattern in the sky that's pretty recognizable. It is not a constellation. It is just part of a larger constellation called Ursa Major. So you can actually see, and you can put on the art if you want. The Big Dipper is really the tail section, the tail and kind of the hindquarters of the larger constellation called Ursa Major, the Big Bear. And again, it's not just those stars that are Ursa Major. Ursa Major actually is a section of the sky that includes all these stars that are part of the actual pattern, as well as some of the others. If I click on this star, I see this is a star in Ursa Major. That's what the UMA stands for. In a similar way, notice that we have a Little Dipper. That's an asterism that is part of a larger constellation called Ursa Minor, the Small Bear. Okay, now let me also point out the fact that I'm going to take off the art here real quick because I find it annoying. But I'm going to advance time as well so you can see the entire Big Dipper. So now I'm just moving time ahead, and notice that, yeah, during the course of the evening, if you stayed out long enough and if you kept on going out and checking, all those stars appear to be moving. And that's something I hope you pick up in the Chapter 2 material, is that all the stars move around this guy, Polaris. That's the only star that remains fixed in the sky. Everything else moves. You should understand why that is the case. Now let me go back to the Big Dipper and point out, as I click some of the major stars in the Big Dipper, they all seem to be relatively close in space, when in reality they are not. They're not even close to being close. And we can actually see that when we click on those stars. Notice that it gives us the distance. So this particular star is called Alkaid, and it is 100 light years away. Here is Mizar, Alcor. That star is 78 light years away. So these guys are, so that star, the light we see from it right now, actually left 78 years ago. For this star, it left 100 years ago, which tells us they must be a huge distance away from each other in space. It just so happens that they appear to be relatively close just by virtue of our perspective. And that's what I'm going to be getting at in the next slide. Okay, so this is just a simulation to reinforce the point that the Big Dipper, what we call the Astros and the Big Dipper, looks like this to us. But that's only because of our position. So I'm going to try to get us kind of lined up so that the stars, kind of look like a Big Dipper from this particular perspective. But if you're, and again, we're projecting these little black dots out onto this celestial sphere. So we're seeing, what looks like the Big Dipper. But notice that's just because of the way we're looking. If we looked at those stars from a different position in space, notice they don't look even, they don't look like a Big Dipper whatsoever. And we can really see the distances between them. So when viewed from Earth's position, they look like a Big Dipper, but in reality, these are stars that are very, very separated in space, with the one at the end of the Dipper, this guy right here, being the farthest away. That star is about 123 light years away. So again, when we look at it in the night sky, we're not seeing that star as it is right now. We're seeing that star as it was 123 years ago. Now, of course, as curious people that you are probably wondering what these numbers are on this grid. You see a 14H and a 13H and a 12H and an 11H, and you see 60 and 55 and 50. Well, hold your horses. You're going to have to wait until next module before we start explaining what declination and right ascension are.
Okay, so stars and constellations have kind of crept into modern pop culture in some cases. If you hear of the Pleiades, Pleiades is actually a star cluster. It's part of Taurus the Bull, but it's a star cluster, sometimes called the Seven Sisters, but it's also known as Subaru. So different civilizations have noticed the Pleiades before, and the Greeks called it the Pleiades. The Japanese, an entirely different civilization, called it Subaru. So if you own a Subaru, if you've ever looked at the Subaru's logo, you'll notice that there are stars there because that is the star cluster we call the Pleiades here in the West. Sirius Satellite Radio, now it's Sirius XM, but what is that logo? It's a star that they make of the dog's eye, right? Well, Sirius is what's called the dog star. And are you familiar with the term dog days of summer? It just so happens that Sirius is a nighttime star in our winter sky. You notice that during the winter months, you'll be able to see Sirius during the nighttime hours, which means during the summertime, it is actually a daytime star. It actually rises with the sun. And the ancients thought that because it's the brightest star in the sky, so they thought that because it was up during the daytime, when viewed from the northern hemisphere, it was adding its heat to the heat of the sun, and that was an explanation as to why the summertime was so hot, and that's where the term dog days of summer comes from. Okay, the magnitude scale. This is actually just one magnitude scale. We'll be learning about the second one later on in the course. This is called the apparent visual magnitude. This is essentially how bright a star or a celestial object appears when viewed from Earth. This has nothing to do with how actually bright these things are. So, for example, and one thing I should mention is that think about this as being a big old number line, extending way positive and way negative. With the magnitude scale, the farther to the left you are on the number line, the brighter the object. So notice the sun, far and away, is way to the left of any of these other objects because it's the brightest. Now, is it truly the brightest star in the sky? Not even close. So why is it so bright? Why does it appear to be so bright? Because it's so close to us. So don't be mistaken in thinking that just because an object appears bright, that it's actually bright. As we're going to learn later on in the course, there is a way of leveling the playing field and comparing apples to apples just by comparing the stars' apparent brightnesses. Sometimes it can be like comparing apples to oranges. It's like a candle can appear very bright if it's right in front of your eye. You take that same candle and take it down to the end of the street and look at it, and you might barely be able to see it. So it appears to have a different brightness depending upon its location, how far away it is. So keep that in mind when you're judging things with their apparent magnitude. It's only how bright they appear when viewed from the Earth. Okay, I'm not a big fan of learning jargon, but you do have to learn some jargon in order to understand the celestial sphere. Now, the celestial sphere is just a model. It comes in handy. It's not really the way things are. The stars are not all attached to this invisible dome that surrounds the Earth, but it comes in handy to imagine that the stars are this way. So we put all the stars on this dome that surrounds the Earth, and what you do is you take there's certain things you can define that. Is what you do is you take the Earth's equator and you project it outward, and it becomes the celestial equator, right? And other things like the geographic North Pole, you project it outward, and it winds up becoming the North Celestial Pole. Where that geographic North Pole, if you take that axis that the Earth spins on, and you extend it outward and let it puncture the celestial sphere, it punctures the geographic North Pole punctures the celestial sphere at the North Celestial Pole. Similarly, the geographic South Pole punctures the celestial sphere at what's called the South Celestial Pole. Now, from any spot on Earth, if you look straight up, that is your zenith. If you look straight down through the Earth, through the center of the Earth, down the other direction, that's what's called the nadir. And one thing you're going to learn is, it's very important to understand, that if you find the North Celestial Pole and drop straight down to your horizon, you'll be looking due north. That's why the North Celestial Pole is so important. Right now, the North Celestial Pole is a star called, or pretty close to a star called Polaris. So if you can find Polaris, the North Star, that will tell you which way geographic north is. So all you have to do is find that star and drop down, straight down to the horizon. That is that's your due north horizon. Now, one thing I want you to pay attention to as you read in the book is how the altitude, meaning how far above the northern horizon the North Celestial Pole is, changes depending upon your location on Earth. Turns out that the angle that Polaris makes with the northern horizon, that angle there, is the same as your latitude. So keep that in mind as you're reading through this chapter.
Okay, so to further illustrate the point, here's a little simulation that's very much like a celestial sphere. Notice we have the Earth in the middle. We have this kind of grayed out sphere. That's our celestial sphere. Let's point out some other things. This yellow line around here, that is what's called the celestial equator. Again, we take the Earth's geographic equator and project it outward. Where it intersects the celestial sphere, we call that the celestial equator, which essentially divides the sky into a northern half and a southern half. We also have, of course, these blue points. Those are your celestial poles. Remember, you take your geographic North Pole and extend it outward, let it intersect the celestial sphere, and you wind up with the North Celestial Pole. Similarly, down here, this other blue dash is the South Celestial Pole. And we've got a guy. This little white disk is essentially we've located our observer being at 41 degrees north latitude. And we're going to talk more when you get into the activity for, I believe it's next module. We'll learn more about latitude and longitude. But latitude is how far north or south you are of the Earth's equator. So this happens to be 41 north. We could go to where I'm more familiar with, Tupelo, Mississippi. That's right around 34 north. So if I'm observing from Tupelo, that would be my location. Now this is a celestial sphere view. I can actually now switch it and show you what it would look like as viewed from Tupelo, Mississippi. And notice I have essentially the same things in my sky. This yellow line is now my celestial equator. This is dividing the northern sky from the southern sky. So I can see a lot of stars in the northern sky, not as many in the southern sky. I can also see the North Celestial Pole. I would have to look due north to see the North Celestial Pole. If I'm viewing it, so now we're kind of looking northward, and I can see that North Celestial Pole. It is above my northern horizon. In fact, it is 34 degrees above my northern horizon. How do I know that? Because the angle above your northern horizon of the north celestial pole is always going to be equal to your latitude. So notice if I switch my latitude, if I increase my latitude, notice how the north celestial pole climbs and climbs and climbs. Until at the North Pole, the geographic North Pole, if I was there, I would have to look straight above in order to find Polaris, because the angle with which the Polaris makes with the north horizon is always going to be equal to your latitude. So notice that from the North Pole, where's my celestial equator? Well, notice it's on the horizon, and so forth and so on. So that's how this whole thing works. Now notice from Tupelo, one thing I can't see is I can't see the south celestial pole. I can't see that south celestial pole because it's below my southern horizon. I can only see above the green here. I can't see stuff that's below the green.